Hello, everyone. Welcome to the SAGD demo for oil and gas production optimization. SAGD stands for Steam Assisted Gravity Drainage. In this demo, you will see how we use advanced machine learning to optimize oil production from two well pairs. In the initial view of the demo, what you are seeing is a dashboard that shows key parameters that optimize oil production. The parameters that generate optimal oil production are pump speed, header pressure, short tube steam, long tube steam, and well casing gas. These are the independent variables to optimize oil production. In this particular view, you're seeing descriptive analytics that do analysis on the input parameters. You can click a particular year or a particular month and see what oil production and water production was in this particular well. This is using Power BI to show or visualize the changes in the input parameters as you change the year or the month. Additional analysis can be done using cluster analysis. Cluster analysis shows you the optimal amount of oil and water produced in these particular wells over time. So here you're seeing cluster combinations, k-means clustering, which means what are the optimal combinations of steam, gas, and pressure that lead to maximum oil production. This will be important for oil operators to determine the optimal combination that have led to maximum oil production and minimum water production from these wells. So one can click these clusters, k-means clusters, and see the changes in oil production and water production based on specific combinations of the input parameters. One can also click particular clusters to see the impact on oil and water production. Another analysis we display is the correlation between oil and water production. What we are showing to the operator or to the user of our solution is how our water and oil correlate over time. So here you're seeing a descriptive analysis of the relationship between oil and water over time. One can also click the year, one can click the month, and see how the relationships between oil and water change over time. That displays the descriptive analysis of oil production data. What we really want to do is get into predictive analytics and show the operator what combination of input parameters such as steam, pressure, and oil are likely to lead to maximum oil production and minimum water production. In oil, we want to minimize the water content in the heavy oil and increase the content of the bitumen. So, into predictive analytics, we have devised a model using our MADS technology to predict how we can increase oil production. So what you're seeing here is the prediction from our MADS model, which is the light blue curve, compared against the actual prediction from this particular well. So you can see the accuracy of our prediction was for oil production was 93.3% accurate. Accuracy for water prediction using our model that MADS has automatically found was also 93% accurate. So these are fairly good measurements or accuracy metrics and tell us that the model that MADS has found, or the algorithm that MADS has found, is fairly reasonable to use. The other screen that we show is optimization scenario. So what we want to, again, do is really help the oil producer determine what combinations of input parameters are likely to lead to maximum oil production and minimum water production. This is similar to what-if analysis. So in this particular screen, we have 6 scenarios. So these are what-if scenarios for the operator to help determine what if I were to, scenario number 1, increase steam in the long tubing by 1% per day and increase steam in the short tubing by 2% per day. Or the second scenario is, what is the optimal oil and water production without any changes in the input parameters? 3, if I were to reduce steam in the long tubing by 1%, what would be the result of oil production and water production combination, and so on and so forth. So if we were to choose, say, scenario number 4, and which is the scenario of what if I were to reduce steam in the long tubing by 1% per day and increase steam in the short tubing by 2% per day, what would be the impact on oil and water production? So what you're seeing on the bottom is a graph that we will play shortly to show you the combinations of the changes in oil and water production based on the optimization scenarios. On the top right, you're seeing the result of this particular scenario to maximize oil production, which in this case is in cubes. So 6.24 cubes per hour is what will result from this well based on this particular scenario. Minimizing the water production will be 11.62 cubes per hour. And the steam to oil ratio is 1.86. So what that particular, this SOR number means is we need 1.86 barrels of water to produce 1 barrel of oil. Okay. If we were to run this scenario, we can see, let me stop this and do that. If we were to run this scenario, we can see the changes in oil and water production, where the y-axis is oil production, x-axis is water production. So as we run this scenario in a what-if, for our what-if analysis, we are able to see the changes in water and oil production if we were to reduce steam in the long tubing by 1% per day and increase steam in the short tubing by 2% per day. The result will be a maximum oil production per hour of 6.24 cubes, as I mentioned, and a minimum water production of 11.62 cubes. If we were to choose another scenario, and run that particular scenario, we can actually visualize what will be the changes in oil and water if we were to reduce steam in the long tubing by 1% and reduce steam in the short tubing by 2% per day. This is a very convenient way of visualizing the changes in oil and water production based on the optimization scenarios, or actually implementing these scenarios in the field. So this is a controlled lab environment. So there you have it. The next screen shows us the results of these optimization scenarios and connecting them to the financial benefits of using our solution. So in this particular screen, you're seeing the optimal oil production as a function of the input parameters that actually lead to oil production. So in this case, we have the Y variable is the oil production, and the independent variables is the optimal steam, header pressure, steam, pump speed, and casing gas. What we want to really show the operator is what optimization scenarios lead to higher financial benefits. So on the top table, you're seeing what is the average hourly flow rate of oil coming out of this well. So in this particular scenario, by reducing steam in the long tubing by 1%, we can see that the average flow rate with optimal variables is 6.24 cubes per hour. Water is 4.3 cubes per hour. What does this result in net present value for this particular well pair? And by the way, we have well pair 2 as well. We can see that the net present value of this well over a 30-year period life cycle of this well is $47.3 million and $9.3 million, $9.1 million without our solution. So the payback on the investment with our solution with optimal parameters versus without optimal parameters is 7 years payback on the investment versus 11 years payback on the investment without our solution. The production rate for using our solution with optimal parameters is 941 barrels per day versus 649 barrels per day without our solution. And the other interesting to note here is that we can increase oil production from 649 to 941 for this particular well pair, and actually do it in using less water. So here we use 1,754 barrels per day of water to produce 941 barrels of oil. In this particular scenario, without our solution, we use 2,325 barrels of water per day and produce only 649 barrels of oil. So you can see that we can produce more oil using less water. And this has certain implications. One, from an environmental perspective, we're using less water, therefore we're taxing the environment less without our solution. With our solution, we're using less water, much more better for the environment, and we're able to actually optimize and produce more oil with lower input going into our operations. So there you have it. This is an application of how advanced machine learning using our MAD technology can really help operators improve their operations by reducing their footprint in the environment and generate more healthier and more profitable results using advanced machine learning. So thank you, and we hope you enjoyed this demo.